This is the optional help video for the Electric Field Lab of Physics 1100. So it's very common with this experiment that you wouldn't have taken the theory in class by the time it's time to do the experiment. That's okay. The experiment was designed such that you could do it before you've taken the theory in class. However, I find that some of the calculations at the end tend to be quite challenging for students. So in this video, I'm going to go through one of those calculations in detail. Now, if you look at the second to last question in the lab manual, you'll see a diagram that looks like this, where there's two electric charges of -2 microcoulombs, and they've been placed on a grid where they say that each grid step is 1 meter long. There's a bunch of different points labeled with letters, and your group is going to be assigned one point, say C or point K or point G, and you'll have to calculate the electric field due to these two charges at that point. So for the purposes of this video, I'm going to calculate the electric field at this point here with the red dot I've just put on here. So this is not one of the ones you'll be assigned, therefore it's safe for me to do the calculation for you. So I'm going to find the electric field at this point due to this charge and this charge. So to make things a little less confusing to look at, I'm going to gray out some stuff on this diagram. So I've done that now. I've grayed out all the letters. I've also grayed out one of the charges, and the reason why is that when you calculate the electric field, you're going to calculate the electric field due to one charge at the point that you've been assigned, and then you'll calculate the electric field due to the other charge at that location. And once you've got those two electric fields, then you add them vectorially. So I'll be showing you this later. For now, however, I'm going to calculate the electric field due to this charge at the location of this red dot. Now, the electric field strength can be calculated using this equation right here. So K is a universal constant. You've been given the value for it. Q is the strength of the charge, so -2 microcoulombs in our case. The absolute values around K mean that you're going to ignore the minus sign. R is going to be the distance between the charge and our point that we're interested in, so the red dot. So K has been given to you. It's 9 times 10 to the power of 9. And as I said, Q is just going to be our charge, so 2 microcoulombs. And the only thing we have to figure out is what is R, so the distance between them. So recall that I said that each of these grid steps is supposed to be 1 meter in length. So we can figure this out using Pythagoras Theorem. So here's Pythagoras Theorem. It's just going to be the x components squared plus the y component squared. So the x component would be 1, 2, 3 meters over. The y component is going to be 1, 2 meters up. So that means we can find r squared using the following calculation. 3 squared plus 2 squared gives us 9 plus 4 equals 13. And that's equal to r squared. Now I could take the square root of 13 to get r, the actual distance between the charge and the red dot. But of course, in my calculation, I actually want r squared. So there's no point in doing the square root. So I'll substitute that in now. So instead of r squared, I now have 13, and that gives me an answer of 1,384.6 newtons per coulomb. Great, so what is that actually? Well, it's the magnitude of the electric field at this red point due to this one charge. We're not done yet, though. We need to figure out what the direction of the electric field is also. Now, that'll be pretty easy because we assume our test charge is positive, and this is a negative charge, so that means the electric field should point from the positive charge to the negative charge. So in other words, it should point this direction. So we now know the electric field's magnitude and its direction for this one charge, but we're not done yet. We still have to figure out the electric field due to this charge at this point. So let's work that out. Okay, so now I've grayed out the original charge and I've ungrayed this second one. So now we're going to do the electric field calculation at this red point for this second charge. So it's the exact same calculations as before, except R will be a different value, and if this had been a different charge, we'd also have to adjust our value of Q. However, since these were both -2 microcoulombs, I can just use the same value up here. So again, we'll use Pythagoras Theorem to figure out how far away this charge is from the point that we're interested in. So our x component in this case will be 1 meter, and our y component will still be 2 meters. So filling that in, we now have 1 squared plus 2 squared gives you 1 plus 4 equals 5. So r squared is 5. So I'll fill that in up here too, and that gives us a value of 3,600 newtons per coulomb. So that's the electric field at this red point due to the second charge. And again, since we assume our test charge is positive and this charge down here is negative, that means the direction of the field is like this, pointed directly from the point that we're interested in to the charge that we're calculating the electric field of. So great, we've now found the electric field due to each of these charges individually, and we figured out its direction. Are we done? No, because we still need to add these two electric fields that we've calculated vectorially. What do I mean by that? That means I need to find the x and y components of the electric field due to this charge and the x and y components of the electric field due to this charge and add them up. Then calculate the total magnitude of the resultant and its direction. So I'm going to do that now. So just to be clear, that means we need to calculate the x and the y components for this right-angled triangle, where the hypotenuse is equal to the electric field strength. So this 1,384.6 newtons per coulomb that we calculated for the green charge. So you probably know how to find the x and y components of something. If, for example, I want the x component of the electric field, then I'd multiply the magnitude by cosine theta, where theta is going to be the angle between these two lines. So that better be what we do next. We find the angle between these two. So we're going to use a bit of trigonometry to do that. The angle, theta, is going to be the inverse tangent of y over x. So we already know that y is 2 meters for this charge and x is 3 meters. So we can fill that in now. So the inverse tangent of 2/3 is 33.7. So we can now fill that in here for cosine theta. And that gives us an answer of 1,151.9 newtons per coulomb. So that's the x component of the electric field due to this green charge. So now we can go ahead and do the y component. So to get the y component, we take the field magnitude and multiply it by the sine of 33.7 degrees, and that gives us 768.2 newtons per coulomb. So that's all the information we're going to need for the green charge. Now we have to do it all again for the blue charge. So let's do that now. So now we're going to find the x and y components of this triangle. As before, the first thing we need to do is actually figure out what this angle is. So again, we'll use trigonometry. The inverse tangent of y over x will give us our angle theta. And in this case, the y is still 2 meters, but the x is now 1 meter. So let's fill those in. So the inverse tangent of 2 over 1 gives us 63.4, and substituting that in here gives us, for the x component, 1,611.9 newtons per coulomb. So that's our x component. We then calculate our y component. So 3,600 times the sine of 63.4 gives us 3,219 newtons per coulomb. So now we've got both the x and y components of the electric field due to this blue charge also. So now that we know the x and y components of the electric field at this red point due to the green charge, and the x and y components of the electric field at this red point due to the blue charge, we can add those up. So here's what I mean. Here's the x component of the electric field of the green charge, and the x component of the electric field of the blue charge. But you'll notice that the one for the green charge I put in as negative, and why is that? Well, if you remember the original right-angled triangle, you'll remember that the electric field pointed this way, so directly away from the red spot over towards the green charge. So that means that the x component of this arrow has to be pointing in this direction, so along the negative x-axis. So that's why I've put in the x component of the electric field due to the green charge as a negative value. The x component of the electric field due to the blue charge doesn't have that issue. It points in the positive x direction, so that's why it's a positive number. So the x component of the electric field due to the green charge is added to the x component of the electric field due to the blue charge, and we get a total of 460 newtons per coulomb for the x component of the total field due to both charges. So now let's sum up the y components too. So here's the y component of the electric field due to the green charge, and here's the y component of the electric field due to the blue charge. In this case, both of these point downward because the field direction pointed towards the charge in both cases, and that's more downward than upward. So that means that both of these values are negative, and so is our final answer, 3,987.2 newtons per coulomb. So that's worth noting, is we had one electric field pointed this way and another electric field pointed this way. That means that the x components oppose each other and cancel out, but the y components actually add up. So now we've got the x component and the y component of the total electric field due to both charges at this point with the red dot. So now we have to figure out what the magnitude is. So we'll just use Pythagoras' theorem for this again. So here's Pythagoras' theorem. It's just going to be the x component squared plus the y component squared, and then we take the square root to get the total magnitude of the electric field due to both charges at the red point. So plugging in our numbers gives us 460 squared, negative 3,987.2 squared, and that gives us a final answer of 4,013.7 newtons per coulomb. So that's the magnitude of our total electric field due to both charges at the red dot. But we aren't quite done even still. We now need to find out the direction that the total electric field points. So let's do that now. So again, we'll use just a little bit of trigonometry to figure out what the angle is of the total electric field. So instead of putting y and x in here, we're now going to put in our y field and our x field for the total electric field. So let's do that. So here's the inverse tangent of the y component of the electric field divided by the x component of the electric field. Notice I've still got that minus sign in there. And that gives us an angle of negative 89.3 degrees. So what does that negative angle mean? It means you're making an angle that's negative relative to the x-axis. So this is a negative 89.3 degrees down from the x-axis. So now we've got the magnitude of the total electric field due to both of these charges and also the direction of the total electric field due to both of these charges. And that's what you need to get the full marks for this question. You need to get the total magnitude and the direction. And as you can see, it's quite an involved process. So I'm going to just recap quickly. So first, you focus on one charge and you figure out what its electric field strength is at the location of the point that you're interested in. You also find the direction of the electric field. Then you focus on the second charge. And again, you figure out its electric field strength at the location of the point you're interested in, and also the direction that the electric field points. Next, you'll need to find the x and y components of the electric field for one of these charges. And in order to do that, you'll need to find the angle that the field makes with the x-axis. To do that, you use a little bit of trigonometry to get your angle theta. Then you do it again for the other charge. You calculate the x and y components of the electric field. In order to do that, you need to get the angle. Then you sum the two x components and the two y components to get the x component of the total electric field due to both charges and the y component of the total electric field due to both charges. And finally, take the x and y components of the total field and use Pythagoras' theorem to calculate the magnitude of the total field, and then again take your x and y components and use them to find the direction of the total field.